The purpose of this demonstration is to show the value of MD contact. In this case, we'll concentrate on glue contact and why do we choose glue contact in this case. First, this looks like an airframe panel with some ribs to it, and it has the value of making assemblies coming from different sources that may or may not have a common nodal boundary to match together and create a model that will be glued together very quickly to make an assessment on performance or even integrate a local modeling within the primary master assembly and avoid having some standalone models and worrying about transferring loads properly, and also retain the stiffness boundary conditions all around as part of the main assembly. So there is no changes or drastic differences or assumptions made when you do that. So we will actually see the value of both of these things and also focus on how easy it is to create some contact bodies and control the different type of contacts we have in this model. We have two primary types of contacts in this model. We have edge-to-edge shells between this refined sections of the main skins, and we will also to the edge contact where we have the boundary to the coarse shells. And we have another type of contact which is face-to-face glue contact. In this case, we're actually standing right at the half thickness of both shells. So physically, if we would expand these and make them true 3D parts, they would be sitting on top of each other just at the tolerance. We have to be careful about the curvature here. This one is flat along the curvature. This one has more discretized refinement. So we have to play with the tolerance here for the detection to occur properly. And that's what we'll show how to do that as well. It's pretty simple. We have a boundary condition set imposed on that model. I'll show you here. We have a pin condition on the top and bottom edges of the coarse shells. At the top and bottom here on the row, we have pin condition, and we have an internal pressure only on the outside surfaces, including the window. So in order to solve this model, we have to define contact pairs. That's fairly straightforward. First, we'll have to define, that's a requirement from the solver, we'll have to define them in order, and the order master-slave relationship of how contact bodies will detect themselves is facilitated if you specify the fine mesh first and you grow towards the coarse mesh. This will actually enable the solver to find the relationship more easily. So what we'll do is we'll start by posting the ribs. We'll define this as the first contact body. Create a contact body. We go to a boundary condition, and we're going to create contact, and we'll pick a deformable body. In this case, we'll create a 2D ribs. We'll pick those elements. We'll create apply. We have dots that shows that each of these elements have been thrown into a contact body. Then what we'll do is we'll take the fine panels as well as the window. This is another thing that facilitates creation of contact bodies. Even though they're not adjoining components, detection will be done at all the boundaries of that self-same contact body. So we'll call this fine shells. And we'll pick all these elements. And finally, we'll define the third contact body as call that shells coarse and be consistent with the name of the group. Also, Patron creates a contact table based on alphanumerical order. So this will help us remember that we define them in that order if we ever have a challenge trying to make contact body pairs detecting each other. So once this is done, we are nearly ready and set up to create the analysis. So we'll call that glue contact demo. It's going to be a full run. We'll run that into solution 101, a linear static run. And we'll specify, in this case, subcase specific parameters that are contact related. So the contact table definition. I'll move this in the window. And we have contact bodies and pairs that we want to actually glue together. So first we'll control the 2D ribs against the fine shells. This is where we have a curvature threshold that we want to make sure that we have detection, because the finer has a radius of curvature different than the coarse one. So we'll put the 0.02 value here. We'll set the detection automatic to help made that as a glue contact. There you go. Then we have the 2D ribs and the coarse, the same thing. 0.02. We don't want to have a release condition in this case. So we double check our pairs. So we want retain the moment between the two bodies here. And finally, we want to actually define the coarse mesh to the fine shell, which is a 2D edge-to-edge contact. And we have to do a little trick here. This is actually to control the gap at the window. We want to make sure that this is small, not too large, so that we don't cross over multiple nodes against one edge or one node on the other side, on the coarse side. So we want to keep this close to close the gap between the window edge and the coarse mesh. We set the same defaults to retain the moment, but we have to define a special contact option in this case, because the bending at the boundary on edge to edge is driven by the neutral axis of the shells. If we don't ignore the thickness, then it will do some funny things and try to reinforce the stiffness, because it will look at the neutral axis and the stress recovery points, top and bottom fibers, and try to apply some bending relationships there as well. So that's why in this case that pair has to be controlled that way. You can actually look into the details in the step-by-step workshop guide for this problem to review that later. So once this is done, we're pretty happy with it. We can create this default subcase. And when we run the model, we can actually create this, make sure that we're running the default. We're going to export the deck called Glued Contact Demo. That's fine. We have the deck here. We can review some of the deck components, make sure that we have these parameters here that make sure that we have released the thickness and make sure that we ignore the thickness in the shell edge to edge contact. Once this is done, we can actually I moved up here. We're going to run our model. Go and pick our Glued Contact demo file. We run it. Run should take about 15 seconds. When we're done, we're going to read the results. And that's also has value in more than just the aerospace typical problems. It has also, you know, any type of assembly mesh that may come from various sources may benefit from that type of simulation. So you must kind of open your mind a little bit to make sure that you see where you can actually apply that kind of simulation technique. So we're going to access the results. By default, Patran recognizes the default names. If we look at deformations on this problem, this is a little bit hard to see, so we'll put element edges on. We'll turn off the show deform. We'll refresh the display to get rid of the glue contact pairs. So we see here that we have a fairly closed model. Continuity seems to be pretty much, you know, observed around all the boundaries, and the displacement shape seems to make sense as well. One thing that can also be done is to request, and let's do that since it's not too long. We'll request the grid point forces. In this case, we can actually do a grid point force balance, a free body diagram of the localized component. That may in some case be very useful. So we'll run Nastran again. So again, we have several examples where we benefit from that kind of integrated global local for electronics components. And the value is that once you have a glue contact model, you can run the typical glue contact scenarios in any of our transient frequency response solutions. So that's also bringing another piece of the benefit. It seems to have run already, so let's access the results for that component and take a look if we have. First of all, let's review again the displacement in a different shape. Let's put shaded here, and we'll not put a fringe on that, and see what it does, so we have a little better view. And this is obviously model size scaled, so it's much more than the actual rotation. So we see an opening here, but that's actually just a visual scaling of the opening. The thing does not really open. When you actually miss the opening, it becomes quite clear, and also you have a discontinuity in the stress field, which is not the case here. If we look at the actual stress field at this boundary, we have continuity in the stress field pretty much. Okay. Now, the one thing we want to show here is take a look at the window local, and we'll do a free body diagram. We have a problem here because my group color, I think, is white on white. Let's change the color of the window, and in this case what we'll do is we'll do a quick plot on the grid point forces. Actually, not a quick plot, but we'll do a free body, this element, and we see all the forces at the boundaries as if we would have done a typical free body diagram. So in this case, you can recover the same thing you would have if you had a different model, and if you're being frequency response, you have like dynamics or transient loads at the boundary, and you save yourself the need to do post-processing on the different model, and also loads transfer, which is pretty time consuming. So that's pretty much it for this demonstration, and I hope that you see a little bit more value than just the typical glue contact in 3D space from 3D to 3D, and this application has a vast array of problems that it can address.